On the left hand side there is a shunt dynamo and some parameters are given. This machine, it is written as 40 kilowatt and 240 volts. Try to understand what does it mean. And armature resistance array here 0.1 ohm and shunt field winding resistance of 50 ohms. That is RF, let's say RF 50 ohms. And then dynamo supplies the load RL, here it is, and while dynamo supplying such a load, it induces such an EMF inside the armature. Beep beep. When the generator dynamo delivers some power, here is an electromotive force given for this condition. And together with, at the same time, when it inducing such an EMF, the output voltage is 240, beep beep beep, here it is, across the load, Vt is equal to 240 volt. In fact, we haven't given any point on this, but we understand that load voltage is, let me say terminal voltage. Terminal voltage is 240 volts. Let's calculate the questions. In fact, there is one thing missed. Here it is given as 40 kilowatts. I don't know what it is. Possibly it is the power of load consuming, but we will go to understand later. Okay, let's continue. What is the armature current? Armature current. Calculate armature current. Houston, I can write Kirchhoff's voltage law around this loop. Here's EMF. Induced EMF is equal to armature current times array plus Houston terminal voltage. Aha, that is given 240 and armature resistance is given 0.1 and armature current beep beep, it is just asked, and EMF was given in the question 255. So 255 minus 240 makes 15. 15 over 01 makes 150 amps. So as you see, it was very easy. Armature current is here. Armature current is 150 amps. We have just calculated. Let's solve the second one. Shunt field current. What is the shunt field winding current? This guy. It was 50 ohms. The voltage was 240. So field current or shunt field current is equal to terminal voltage over R field or shunt field. This guy. 240, it is given. It is directly connected to terminal, as you see. So over 50 ohms makes, let me calculate, 240 over 50 makes 4.8. 4.8. You cannot see perhaps in the screen. It is 4.8 amps. The second answer is shunt field current is 4.8 amps. Now, ladies and gentlemen, third question, what is the load current? Houston, take care. Here's an 150 amps come in to the node and 4.8 is missing down here. Rest of the current supplies load. So it is very easy. Load current is equal to armature current minus field current. That is DC. There is no phase displacement. 150 minus 4.8 makes what do you 5.2 possibly. Yes, here it is given. That is the load current. As you see, it depends the connection diagram we have already discussed here. If you cannot imagine connection diagram, you cannot write proper Kirchhoff's current law or Kirchhoff's voltage law. To write those relations, you should consider or draw proper diagram first and then equivalent circuit. That is important, and that example emphasizes this. And now, what is the power delivered to load? What is the power? Houston, delivered power is equal to terminal voltage times load current. Here in this example, it was 240 volts. It is already given in the question, because to have this, a machine induces such a high voltage, but there is only 240 voltage drop here across the load. And the current is, as you solved, 145.2 amps. So load current times voltage terminal makes the load power. That is the power delivered to electric load. It is approximately 34.8 kilowatts. 34.8 kilowatts. It is very lyric question, an easy question. There is no trick in the question. There is no hidden parameter behind. Everything is very clear. By emitting mechanical losses, calculate required input mechanical power. Let me write it down here. Neglect mechanical losses are neglected, omitted, and then calculate required mechanical input power, because that's the generator input power. Ladies and gentlemen, you apply some mechanical input power. Here would be some mechanical losses. Rest of the power will be converted into electric power. Some will be lost. Let's discuss the connection diagram. You apply input power, that is a generator. Here would be some mechanical losses, and then here's armature resistance. Here would be some losses, beep beep. Here would be some copper losses in armature, and then here would be some copper losses in shunt field coil, So here would be copper loss in field coil. Rest of the power is delivered to load. Okay, here's the load power or electrical output, mechanical input. This is a shunt dynamo. Just imagine the power flow. In the question, mechanical losses are neglected. So that is the converted power across the armature. Ladies and gentlemen, there is an energy converting device here. That device is converting energy. It is armature. And we have defined that armature is the place where the electromotive force is induced or where the energy conversion is occurred. So what is the energy or power across this element? Armature EMF times armature current. Let's say armature power. Ta-ta, ladies and gentlemen, that is induced power or converted power. That is converted power. Always the power across this element is induced or converted power. If it is generator, that is the power converted into electrical energy, or if it is motor, that is the power induced in mechanical power induced in the armature. You know, motor is a device converting electric energy into mechanical energy. So this guy converts electric energy into mechanical energy. That is the armature, making energy conversion. So armature power can be written as like this. Copper loss can be written as like this. Field copper losses can be written as field current squared times R field, and terminal output power, load power, can be written as load voltage times load current. That's it. And mechanical input power can be written as mechanical torque and angular speed of the shaft. That is the power equilibrium of generator. And then, what was the question? By omitting mechanical losses, please calculate required mechanical input power. Houston, we should write the equation. What is the mechanical input power? Mechanical input power is equal to this guy, which is mechanical losses. We say in Turkish sürtünme ve ventilasyon, plus copper losses in armature, plus copper losses in field coil, plus output power, load power. Now, ladies and gentlemen, we should calculate that elements individually. Some of them already calculated. We have calculated, it was something like that, I think. But we don't know those guys. We will calculate, and this guy is neglected. So that is the required input power. Let's examine the solution. Here in this case, armature power, it is written different, no matter. Let me show you. You can also write these node equation. Mechanical input power is equal to mechanical losses plus armature power, induced power. So it can easily be written, instead of calculating those three together and summation of those three, you can simply calculate only this guy. Writing only this node equation is easy and enough. mechanical input power is supplies mechanical losses plus converted armature power that is neglected, so it is equal to armature EMF times armature current, that is PA, armature power or converted power, that is equal to mechanical losses, since mechanical losses are neglected. Let's examine armature power 255 times 150 amps makes such an electric conversion in armature, so required input power will be this. That is very lyric, but you should make some operations on power balance diagram. You should know whether this guy is minus or plus. For example, if it is if it is motor, you supply here. Let's talk about motor, shunt motor. You supply electric power, and then here is copper loss in field coil, here is copper loss in armature, and then rest of the power will be converted into armature. Some mechanical losses will be missed here, dissipated, and then here is mechanical output. The equation for this node, mechanical output, is equal to PA minus PM mechanical losses. Here you see it is minus, but here it is positive. You should consider the operating and power balance, otherwise you will have a mistake. You should take care on this. And final question is the efficiency. Efficiency, there is no need for further explanation. Any system has an input, has an output. So such a system efficiency can be written as output over input power. What is the output for this machine? It is a generator, so output power is the load power. Where was it? Here it was. That is the load power, delivered the load, and that is the input power applied in terms of mechanical power. So output power over input power makes a 91% efficiency for this machine. Ladies and gentlemen, it is a lyric question. You should understand this guy better.